Great to see you here again in this new presentation. In this presentation, we will look at a very famous theorem, which is called Fermat's little theorem. Now, when we look at the theorem itself, first of all, I have to say that it originated by a French mathematician who was active in the 17th century. His name was Pierre de Fermat, and he made many discoveries in the field of number theory. There are a lot of the discoveries he made that have been proven, but not all of the theorems that he described have been proven yet. So there's still open problems that exist. And like we've seen before, some of those open problems are in fact sometimes accepted because we didn't find a counterproof yet. Although we are not sure that they're valid for all possibilities, so we always have to be careful when some things have not been proven for all possibilities. Now, the interesting about Fermat is that one of his theorems is called Fermat's little theorem, and it is in fact a formula that can be used to find large prime numbers. And large prime numbers are very important when we are talking about encryption. Encryption is based on prime numbers, about factorizing large numbers into large prime numbers. And of course, we want to find those large prime numbers in order to encrypt in a very secure way. And of course, we have to find ways to decrypt, but that's what we will see in another paragraph later in this chapter. Now, what is the theorem? What is Fermat's little theorem saying? It says that when we have a prime number p and an integer which is not divisible by p, then we can say that a to the power p minus 1 is congruent with 1 modulus p. And we also have for every integer a, we have the congruence a to the power p is congruent with a modulus p. Now this is obtained by multiplying the congruence a p minus 1 congruent with 1 modulus p with a. We've seen that before, that we could multiply those congruences. Now the same thing is in fact that when we have a theorem which is in fact saying here that when we have a, which is an element of zp, p relating to the prime number that we selected, then a to the power p minus 1 is equal to 1 in zp. So basically, when we look at the congruences, we see that when a is compliant with this condition, we also can say that a p minus 1 is congruent with 1 modulus p. Now, we're not going to prove the theorem here, but we're going to look at some applications. And for example, the theorem can be used to compute a to the power n modulus p, in which p is a prime number and p does not divide a. So it also means that the greatest common divisor between p and a is 1. The first step is to find the quotient and the remainder when n is divided by p minus 1 using the Euclidean algorithm. And based on the properties of divisibility, we can write that n is equal to the quotient multiplied with p minus 1 plus the remainder. So we are using the division of divisibility here, and we find the quotient and the remainder of the division. When we replace the expression of n in a to the power n modulus p, we can rewrite it as a to the n is in fact a to the power q times p minus 1 plus r. And in fact, we can say that it's also equal to a to the power p minus 1 to the power q multiplied with a to the power r. We'll just applying the properties of powers here. And when we put that in the modulus, we can say that the fact that a to the power p minus 1 is in fact 1 modulus p. And when we have that 1 to the power p, of course, it will be 1. So we still have a to the power r, which is congruent with a to the power r modulus p. So basically, when we are calculating those large powers, we just calculate the modulus of AR modulus P. We just look at the remainder that we have found for this calculation. So this simplifies the way we deal with this power. Let's have a look at an example of Fermat's little theorem, and we consider the following expression: 9 to the power 333 modulus 13. So in fact, we want to find the solution of this. In order to calculate, we first find the remainder of 333 divided by 12, which is p minus 1, or we express 333 as 333 is equal to the quotient times 12, p minus 1, plus r, the remainder, and we find that we can say that 333 is equal to 27 multiplied with 12 plus 3. So the remainder is basically 3. Now we can rewrite 9 to the power 333 modulus 13 as 9 to the power of 333 is 9 to the power 27 times 12 plus 3. So we can say that is 9 to the 12th to the power 27 multiplied with 9 to the power 3. And from the little theorem of Fermat, we can say that 9 to the 12th modulus 13 is in fact 1. And finally, we can say that 729 is congruent with 1 modulus 13, which in fact results in the fact that 9 to the power 333 modulus 13 is equal to 1. So basically, we can use the theorem to calculate these powers very quickly and without exceeding the calculation capacity of the computer programs. So we don't have those overflows in the numbers, which is of course very important. Now, when we look at the prime numbers and we look at Fermat's little theorem and prime numbers, there are some interesting conclusions we can provide you. We looked at the previous videos when we looked at also at the sieve of Eratosthenes. We showed that an integer n is prime when it's not divisible by any prime p smaller or equal than the square root of n. This property is true, but it's not really very efficient when we have very large prime numbers. And it's very important that we could find a better way, a faster way to identify large primes. Now, when we look at the Chinese mathematicians, there are some sources stating that they believe that n was an odd prime when we could say 2 to the power n minus 1 is congruent with 1 modulus n. For example, 2 to the power 7 minus 1 is in fact 2 to the power 6 is 64, which is congruent 1 modulus 7. So here we see that we, let's say, never found a value of any prime number that we considered of being a composite, which is a composite integer for which this congruence holds. So basically, we could find that this is in fact an element which is quite important. So in order to say that we have a prime, the 2 to the power n minus 1 is congruent with 1 modulus n. So basically, we can find those prime numbers. Now, what's when we look at pseudo primes base 2? Unfortunately, we can find composite integers for which this congruence is also valid. Now, when we look in these cases, when we find a composite integer which complies with this congruence, then we can say that this number is a pseudo prime. Now, pseudo primes are not primes, and we can find them. We have to find for every expression of n, for every prime n that we consider, we basically have to verify if it is a prime or a pseudo prime. Let's have a look at the integer, which is 1729, which is basically as a composed number composed of 7 times 13 times 19. And we can prove that this is a pseudo prime to base 2 by putting it in the expression. So we say that 2 to the power of 1729 minus 1 is 2 to the power 1728 is congruent 1 modulus 1729. Now, when we look at this, we can say that 2 can be written as 2 to the power 6 multiplied by 288. So we find here 1 modulus 7 is congruent with 1 modulus 7. So that's the first element that we take. We look at the first prime, the 7. So we can write this congruence. Now we find for the second case, for the second prime, 13, we can say 2 to the power 12 to the power 244 is congruent 1 modulus 13. And the last one, 2 to the power 1728 expressed as 2 to the 19th minus 1. So we find, in fact, that is equal to 2 to the power 18 to the power 96 is congruent 1 modulus 19. So basically what we have here is that all those elements together, we can find that in this case, we can conclude when we multiply all of them that 2 to the power 1728 is congruent with 1 modulus 1729, which in fact means that we conclude from the formula that this would be a prime, but basically what we have found that, or we already knew, that it's not a prime number. 1729 is not a prime number, although the congruence holds. Since it's not a prime number, we consider this to be a pseudo prime. Now, these were the pseudo primes with a base 2. It's also possible to expand the pseudo primes to different bases. So let's say in general a base A. Now, when we look at those primes, we can define in general with B a positive integer and N a composite positive integer, or sorry, A a positive integer and N a composite positive integer. We can write the congruence. A to the power n minus 1 is congruent with 1 modulus n, is valid. And then we call n a pseudo prime to the base A. Of course, when it's not a prime number. In case it's really a prime number, then we can say that it is, of course, a prime number. But in the case it's not a prime number, we call it a pseudo prime to the base A. Now, both prime and pseudo prime numbers will satisfy the congruence. So based on this congruence, we cannot say, is the number a prime or a pseudo prime? Like I said before, we have to prove for each of them if the result is prime or pseudo prime. Now, after concluding the tests, we can only conclude that the number is a pseudo prime and possibly a prime. So these are the two things we get out of this test. Now, for lower numbers, it's very easy to verify, but with large numbers, this can become very complicated. We also have some other special numbers, and we call them the Carmichael numbers. And the Carmichael numbers are special numbers which comply with the following statement. Consider a composite integer that satisfies the congruence a to the power n minus 1, congruent with 1 modulus n, for all positive integer a with the greatest common divisor of a of n is called a Carmichael number. Now, when we look at the previous exercise, we can also conclude that the number 1729 is a Carmichael number. Now, we see that 1729 is 7 times 13 times 19. We have the composite integer, and we look at the different prime numbers that we considered. So we could say that a to the power 6 is congruent with 1 modulus 7. A to the power 12 is congruent with 1 modulus 13. And a to the power 18 is congruent with 1 modulus 19. So it has a greatest common divisor for all the different composing prime numbers, which is equal to 1. And in that case, we say that this number is a Carmichael number. So here we saw a very interesting application of Fermat's little theorem. We also found out how we can define pseudo primes, and of course we also defined the Carmichael numbers. The next session we will look at what we call primitive roots and discrete logarithmics. You're doing a great job, and I'm looking forward to seeing you in the next video. Thank you, and bye-bye.